In this video, I'm going to discuss the term supermoon and also talk about solar eclipses. We're going to be focusing on the angular nature of objects in this video. And let's find out, what is the astronomical basis for the term supermoon? It is a little bit of hyperbole, a little bit of hype, and we'll discover that. So when we're interested in supermoon, a moon that's larger than average, we need to calculate the angular size of the moon on the sky. The equation that governs this is the central angle formula, S equals r theta. If you think of a sector of a circle, I'll just draw a little one here. Sector of a circle, we have the radius of the circle, S is the arc length at the end of the sector, and theta is this central angle back to the center of the circle. So S equals r theta. S and r need to have the same units, so miles or kilometers, and theta will be measured in radians. So we're interested in the theta value for the moon. So I rearrange this and solve for theta. Theta is equal to S divided by r. S, we're going to use the diameter of the moon, and r, the distance of the moon from the Earth, which is essentially the distance to the observer. Even though we don't live at the center of the Earth, here's a little diagram. This diagram is definitely not to scale in many respects. The size of the Earth and the moon are not correct, and especially the distance between the Earth and moon are not correct. The moon is about 60 Earth radii away from the Earth, so it's much too close here. I didn't have a big enough page to show it to correct scale. But here's our Earth. Here's an observer, and this observer is way too tall in this drawing. Humans, it would take about 3 million humans to go from the center of the Earth to the surface of the Earth, standing on each other's heads. About 3 million. Humans are very small compared to the Earth, but just for purposes of illustration, we have a human here looking at the moon rise, and in this situation, we have a certain angular size for the moon. The diameter of the moon, this is an approximation, 3476. I think it actually might be closer to 3475, but I just doubled the radius. That was a rounded value, so I'm going to use 3476. The moon's path around the Earth is not a circle. It's more elliptical shape, and not a perfect ellipse either, but we have a situation here where the moon gets as close as 3.63 times 10 to the 5th kilometers every month, but not always at the phase of full moon. And the moon is far from the Earth in its path, 4.06 times 10 to the 5th kilometers, again every month, but not always at new moon or full moon. That shifts around during the year. We won't go into all those details, but calculating now the angular size of the moon when it is far from the Earth in its orbit. So I put in the moon's diameter, the 3476. It's not the arc of a circle, it's a straight line, but at the distance of the moon from our observer here, that's a very minor correction. We're going to ignore that fact that S should be the arc of a circle, but we're using a straight line distance of diameter of the moon. The distance to the moon at this time at apogee, 4.06 10 to the 5th kilometers. If you need any help working with powers of 10 notation, you might want to view my other video on powers of 10. But use your calculator and you get this many radians. For ease of conversation, radian is not an easy concept in our minds. Degrees work a little bit better for me at least. So I'm converting this. The conversion factor is 180 degrees. I have the same angular measure as 1 pi radian. So the radians get canceled off here and we're left with degrees. Turns out to be just slightly less than half a degree, 0.491 degrees. This is the apparent angular size of the moon when it is far from the Earth. Of course, the moon does not change its physical size, but to our eye, it's further away, so it appears smaller. Its angular size is smaller. Then at perigee, when the moon is close to the Earth in its orbit, same diameter of the moon, but now the distance to the moon is different. It's smaller because we're close to the Earth. and we get a different number of radians, a larger number, because our distance is smaller. And converting that, we get 0.549 degrees. So that is our angular size of the moon, excuse me, when the moon is relatively close to the Earth. And if you want to do a percent difference calculation, if we subtract these two numbers and then divide by 0.491, we find that the moon is roughly 12% larger to our eye, apparently larger by 12% at the time of perigee compared to apogee. So this gives us what, quote unquote, a supermoon. Super meaning a little bit larger, 12% larger, and it's also a little bit brighter because it's closer to us. So there is the supermoon. It's interesting, occurs about once a year. The full moon would be larger than average, and there's a gradual shift. There will be a full moon also that's smaller than average, and I don't know if it has a name. Probably not, because it's so newsworthy. Okay, let's move on and talk about solar eclipses. It involves the moon as well. So we've discovered that the moon changes its angular size as it moves in its path around the Earth, and from 0.491 degrees to 0.549 degrees, the moon is smaller or bigger to our eye on the sky. The angular diameter of the sun also changes because the Earth does not have a circular orbit. It has an elliptical orbit. Sometimes it's closer to the sun, sometimes it's farther away. Do you know, in the northern hemisphere, it's cold in January. Do you think the Earth is close to the sun or far from the sun in January? The answer is close to the sun, because our distance from the sun does not change dramatically. It just changes a little, and the tilt of the Earth is much more important. I'm not going to go any further into that. Look in an astronomy book or look online for the reason for the seasons, and you'll discover the tilt of the Earth is much more important than the change of the distance from the sun to the Earth. But here we go. So again, we're going to be calculating this angular size of the sun using theta equals arc length divided by radius of the circle. And we have two calculations to perform here. At aphelion, when the Earth is far from the sun, then we take the diameter of the sun, worked it on the top, 1.3914 times 10 to the 6 kilometers, and dividing by the number of kilometers that the Earth is away from the sun at this time. This is not the average distance of the sun from the Earth. This is at aphelion, when the Earth is farthest away in its ellipse. We get a number of radians. Again, we'd rather talk about degrees, so we have this conversion factor. 180 degrees is 1 pi radians. 3.14156 is our value for pi, roughly. And doing that calculation, we find that at aphelion, the size of the disk of the sun, where it's the photosphere, the part of the sun that's emitting light, the angular size of that disk is 0.524 degrees. And then at perihelion, when the Earth is closer to the sun, put in the distance of perihelion, convert it to degrees, we find 0.542 degrees. So these are our angular size of the sun on the sky, and up here are the angular sizes of the moon on the sky. When the moon is close to the Earth, 0.549, and notice that that's larger than the apparent size of the photosphere, where the visible light's coming from the sun. So if we have a situation where the Earth, moon, and sun are directly in a line, when the moon is at this position, we can have a total solar eclipse. The disk of the moon on the sky is larger than the disk of the sun. Of course, the sun is tremendously much larger than the moon, but its apparent size on the sky that's important. And the angular size of the moon's disk is large enough when the moon is close to the Earth in its orbit. It is large enough to cover the sun at both of these conditions of where the Earth might be in its orbit. But notice if the moon is far from the Earth in its orbit, It only covers 0.491 degrees on the sky, and you will not get a solar eclipse, a total solar eclipse, at any place in the Earth's orbit. So I'm recording this in 2017. In early 2017, there was an annular eclipse of the sun. Annular meaning that the disk of the moon was smaller than its apparent size, than the apparent size of the sun's disk. So the moon could not cover up the whole disk of the sun. Another way to look at it is the shadow of the moon. And I'll go ahead and draw it here. So here's the Earth, sun out here. Again, very much not to scale, but here's our moon. And for the case of the annular solar eclipse, the moon's shadow does not reach all the way to the surface of the Earth. The moon is too far away, so let's put this at apogee. The moon is too far away for its shadow to reach the Earth. Another way that these calculations show to say this is that the angular size of the moon is smaller than the angular size of the sun. So that was early 2017 when that occurred. And in August 21st of 2017, there's a total solar eclipse of the sun. If you're watching this video before that time, if you live on anywhere near a line from Oregon to South Carolina, you should start making plans as to where you will drive to see the total solar eclipse, because the moon will be big enough to cover up the disk of the sun. And again, talking about sort of seasons, the Earth is close to the sun in January. The Earth is far from the sun in July, 6 months later. And August is kind of near July. So we're going to be in a situation where the disk of the sun on the sky is smaller because the separation between the sun and the Earth is greater in August than it is in January. So it's a little easier for the moon to cover up the sun because the sun apparently is smaller in the sky. It's further away from us. And we will get a total solar eclipse. So that's our summary of why we get eclipses. Sorry if I did not have this up here earlier. At the perihelion, the angular size of the sun on the sky, 0.542 degrees. And just a little summary, the angular size of the moon changes, the angular size of the sun also changes. Our best situation would be when? Is the moon close to the Earth or far from the Earth to get a total solar eclipse? Your answer should be close to the Earth, the aphelion that has the 0.549, sorry, perigee, and the moon is 0.549 degrees on the sky. And what's the condition for the Earth and sun separation to get a total solar eclipse? What's the best situation for the Earth and sun to be close or Earth and sun to be far away? And your answer should be far away. We want the disk of the sun to be smaller so it's easier for the moon disk to cover up the sun's disk. So that's a little bit of a explanation. Hope I didn't confuse you with that last part here. Our best conditions for a total solar eclipse is when the moon is close to the Earth, but the Earth is far from the sun, giving us a apparently larger moon and an apparently smaller sun. So it's easier for the moon to cover up the sun. Ask your instructor if you are confused by any parts of this, and keep reading astronomy textbooks.